try to use whatever is available, cheap and maybe free. A lot of this stuff is laying around that people don't know how to use. Factory cast iron exhaust manifolds are everywhere. S5, S4, third gens. Can't really use the third gen because of the twin turbo setup, but any of the single turbo setups, you can use the OEM turbine housings, which actually are quite generous as far as AR is concerned, and bore them and put larger turbine wheels and turbochargers. There's a couple of companies that do upgrade on the compressor side, but they leave the turbine alone. That in itself, the results are fantastic, but that in itself ends up choking the motor prematurely. You end up saturating the total volume that can flow through that turbine short of 8,000 RPM. And what's the purpose of a rotary engine? You know, to really spin the crap out of it. That's where the real power is at. That's where the fun is at. Compare, this is a Hitachi HT28, I believe. Compare that and that to, this is a Garrett P wheel. Huge difference. This wheel will support, well, it's the most popular wheel for a 13B, but this wheel will support 600 horsepower. This wheel will end up choking the motor short of 8,000 RPM.
You say choke the motor, what do you mean by that?
Choke the motor means that it develops back pressure, and the engine can't overcome the back pressure. Normal on a street engine, your normal boost to back pressure is about 2 to 1. That means that if you're at 15 pounds of boost, if you measure the back pressure between the exhaust port and the turbocharger, it's about 30 pounds of back pressure. That's about normal. You need back pressure to drive the turbocharger to spin it. On a race car, you want to get down to more of a 2 to 1. Rather 2 to maybe 1, maybe 0.75. Ideally it would be 0, but that's impossible. If you have 0 back pressure, you can spin a turbocharger. So the idea here is to basically try to reduce the back pressure so that the engine can continue breathing before the exhaust starts backing up into from the exhaust into the intake system, saturating the intake, and cause premature detonation, and simply just cause the engine from having a clean and dense enough air mixture to continue running. That's what I mean by choking the motor. Same thing happens with when you build a ported motor and you don't upgrade the exhaust system. You get somewhere on the line and the motor just it can't flow no more. Same thing happens with the turbocharger. The mill right now is on automatic feed. And we're going to take a very, very slight cut across the loop of the extruder. Probably going to have to change the cutter to a longer one because the boring head is going to end up hitting the turbine housing. This turbo application that we're building here is specifically for the RX8 project. Because we're trying to do this for the enthusiast that wants to do it as on a kit basis. This is a very good way to go ahead and locate the turbo that will more than satisfy the requirements of the airflow of the engine, yet at the same time not have to spend an extreme amount of money in making it all come together. We're going to stop. You can take a good turbo. There's a lot of good turbos out there. You don't necessarily have to have rotary engines by nature put out so much exhaust energy that ball bearing turbochargers are really not necessary unless you're really going, you know, all out and building something for maximum power. My philosophy has always been to stay small, contrary to popular belief, stay tight on the turbine housing AR ratio to get instant spool up, and then have multiple wastegates, absolutely multiple wastegates. One large one will suffice up to about 500 horse. A very large one, I'm talking about you know, 55, 60 millimeter. You're better off to have multiple wastegates because you prevent what is known as boost creep, where the turbo will get to a certain point, stay there, and then as the RPM increases, back pressure builds up to the point where the wastegates cannot dump enough and the boost keeps going up. That's bad because if the motor ends up not being mapped to a point where boost creeps develop, especially on a cold night, weather drops, temperature drops, density goes through the roof, all of a sudden the motor goes lean. When you get some boost creep, motor go. So anyway, there's a lot of turbos out there, especially these wholesale turbochargers. They're excellent turbochargers. They have Inconel turbine wheels and shaft. They're designed for diesel trucks. They meet the breathing capacity or the airflow capacity of a rotary engine perfectly. And you can buy them brand new, relatively inexpensive. And anyway, you take a whole set, or you take you know, a Garrett or anything but an eBay turbo. They'll work for a couple of weeks. Anyway, get a turbocharger, bore the housing, put it onto your stock exhaust manifold, stock housing, and you saved yourself half the money of a turbo system. Obviously, you need intercooler, piping, the rest of the fuel system, everything to support the horsepower. But as far as the turbocharger is concerned, exhaust manifolds, there's a lot of exhaust manifolds out there that are beautiful, they're aesthetically beautiful, but they're crap because the port runners are extremely large in diameter. So the exhaust loses velocity. It takes a long time to get the turbo to spool up. And the reality of it, a street race is from red light to red light. It's not a half-mile long. So you don't have the luxury to wait till the motor is at 7,000 RPM before the turbo comes up on boost. You want full boost by less than 3,000. That's how you win a street race. You want to build a race car? Then none of this applies. This is for street applications.
One other question about the cost of doing the modifications you're doing here to these cheaper, less
Well, you can find a damaged S4 or S5 turbo, pick them up all day long for, you know, I picked up the donor turbo that gave me that turbine house. I picked it up for $35. Got a perfectly good exhaust manifold and a perfectly good turbine housing. This turbocharger bought it brand new for $490, brand new. It came with a diesel turbine housing that I can't use, which is humongous. Puts a turbo somewhere where it will not fit within the confines of the engine compartment. So we're basically taking the cartridge and the compressor housing and putting them on the OEM Mazda exhaust manifold and turbine.
So how much does the modification you're doing cost for
any machine shop can do a boring modification like that, depending on how accurate they get it, how much time they dedicate to the setup. Less than $150.
Okay.
Bullseye housing, brand new, made for that turbocharger, which is very popular. A lot of the Nissan guys use them. It's beautifully tailored, flow-wise and compressor CFM-wise for small engines that are developing somewhere short of 500 horsepower. This is a Bullseye housing made specifically to take the diesel housing off and use that cartridge on a T3 flange. They also make it for a T4 flange. That housing is $375. So you can basically bore an OEM turbine housing to accept that turbocharger. So once the shop that you take it to knows what they're doing, and save yourself a lot of money and end up with a beautiful package, very small, very tidy, that will support, you know, the horsepower for the speed that most guys are looking for. The purpose for doing this boring modification is to put a much larger turbocharger onto an OEM RX7 Turbo 2 S5 turbo turbine housing and exhaust manifold. As you can see, this is the size of the impeller that comes stock on the S5 Turbo, and this is the impeller that we're going to be putting in there right now.
Side by side?
Substantially different. Huge difference. Flow-wise, this impeller can sustain over 500 horsepower. This little impeller here has been pushed by some people with a larger compressor wheel upwards of 350. The problem is that it's quite small. It ends up choking the motor, and you end up putting a lot of heat into the engine. So there's no sense trying to achieve the power with an extreme amount of boost when you could do it with a much more efficient turbocharger, larger turbine wheel, larger compressor wheel. But the actual housing itself is a fantastic design. It's got two integral wastegates built in, and it's a dual inlet, so each rotor pulses, and therefore the lag time is reduced dramatically. So by putting a much larger turbine wheel, we'll be able to get up to speed and handle the volume of a very high output motor with the stock turbine housing. This housing, by the way, is a 1.0 AR ratio. It's a 0.5 on both sides. So it's actually quite large when you consider the total area that's inside of it. We're also going to combine this with an extra small, like a 44mm wastegate board and tap into the exhaust manifold. The whole idea is basically to get instant, and I mean instant, throttle response, full boost by 2,500 RPM. And if the turbine housing gets saturated, which I don't think it will, but if it does, we'll have both the built-in wastegate, which goes on both sides of the scrolls, and an additional external wastegate. This setup can be made very simple. Parts are readily available, and you know, you can drop in a substantially larger cartridge into this turbine housing and have the best of both worlds. Use a factory manifold, factory turbine housing. It sits far forward and low, so you know, on a third generation engine, the turbocharger, actually the compressor that we're using is quite large. It's about the size of a T70, and there's no interference whatsoever. So it should be a real nice piece of equipment when we're done, and the results will speak for themselves.
How many passes do you think you're going to take?
Oh, this is going to take a good 4 or 5 hours to do it.
Yeah, because those wheels are a lot bigger.
A lot bigger. To say we don't get a second crack at it. Oh my God! No. See, what is it they say? Necessity is the mother of invention.
That's true.
Oh, I got lucky. Throwing down.
To have the right tools, huh?
grind it off on, you know, file it off. Nothing more restorative. Smooth as a baby's butt. Well, that was an unexpected success.
That's HCAEastFloridaJobs.com.
Alright, perfect. It fits inside. Now all we gotta do is just bore it ever so slightly so that the actual cartridge will drop in. Very, very, very minor. Once I cut that seat to the exact dimension of that inner bevel, she'll go in. That's it. It could stand to have maybe thousands of an inch per clearance, but as long as you can spin it.
Yeah. Success, man.
That's it, brother.
Better to be a little too loose and way too tight.
Better to be way tight than too loose, because if it's too loose, the whole thing can move around and have the impeller
Man, it only gets worse as it moves around.
contour of the vane is dead on the money. Would probably been slightly tighter.
So, does it spin in there okay?
Spinning absolutely beautiful. The clearance identical everywhere, but the real critical part when you're doing some kind of a hybrid deal like this is, you know how the turbine wheel has that that contour from the inducer to the exducer.
Yeah.
The contour has to match that contour. Right there. You see that contour there and that contour there? Mm-hmm. And I have a special cutter to dress that up if there's just the slightest mismatch in calculations, but from looking at this, it's like maybe a couple of 3/1000ths of an inch clearance. That's what I'm saying. I'm surprised it's not just touching ever so slightly, because usually you would just touch a little bit and then you just dress it down a few thousandths until the clearance goes away, but this is just dead on.
The first time?
Absolutely dead on. Yeah, and on the first try. I should go play the lottery tonight, huh?
Yeah, I would think so, yeah.
Well, there we have it. This is a Holset HX35, which is a fantastic, absolutely fantastic turbocharger. Suits the requirements, the flow requirements of a rotary engine, fantastic. Very healthy turbine housing, and we made it fit in there absolutely beautiful. And then the compressor is actually that compressor wheel will sustain easily 450 horse, 430 horse. It could probably go a little bit more, but you're just starting to beat up the air. Although the Holster turbos are designed for very high pressure ratios, high boost. So a slightly larger compressor wheel will definitely get you into the 600 horsepower range. It's quite a bit bigger, but it's a 6-blade wheel. No, 7-blade too. 1, 2, 3, 4, 5, 6, 7. Yeah. I like the 7-blade wheels. They're very instant to respond. The 6-blade wheels will actually make a little more power way at the top, but they don't produce that initial punch. You can buy this wheel already with a machine housing to put the HX40 compressor wheel on the HX35. The problem with the HX40, it's got a smaller turbine wheel, which would actually give us a little bit larger AR ratio, but the flange on this side doesn't lend itself to being able to bolt it down. I've been working on an adapter. It's just one of those ideas that, you know, you come up with and never have time to play with. It's a lot easier simply just to change the compressor wheel. But let me show you what the turbine compressor housing is. Now this is impressive. That's the size of your compressor housing. As compared to the Garrett unit or a GT35, quite a bit smaller than this. I have one here, actually, and that's the HX35 compressor.
So area and radius 7.70 is what?
Well, 0.7 is pretty much standard for compressor wheels, but for turbine wheels, how you tailor the speed of the turbocharger and the boost and the response is by adjusting the AR ratio on the turbine housing. A smaller number means it's a tighter housing. It'll come up much quicker, but it'll choke the motor.
That's
a larger
right.
number, there's more area to it. It'll be slower to respond to spool up, but it'll make more power. More horsepower at the top. My philosophy has always been to run a tight housing, even if it's tight enough that it'll choke the motor. We run multiple wastegates on each rotor. Therefore, you saturate the turbine instantly, and then you dump the excess on a per rotor basis. That makes for the best throttle response, transient response, and all the power that a much larger turbine housing will do without the lag.